So this is your first lecture on relative motion, topic being relative motion in one dimension. And the important thing to understand here is this, that in order to study relative motion, we need to first formulate some basic rules. Basic rules for what? That we will understand. But first of all, I want you to keep your focus on this grid. You can see there is a grid of squares. Some might not look as perfect squares, but okay, that will make do. Each grid has a square module of length d and width d. And we also have a compass. The compass tells us in what direction we are moving. So if we are moving towards right, we will say we are going towards east. Towards left, it will be west. Upside on the screen, that is north, and downside on the screen, that will be south. So now I have 3 participants with me, or let's say 3 persons. So let's say this is my person P1, and let's say this is my person P2, and let's say this is my person P3. These are the 3 persons that I'm interested in. Now the question is quite simple actually. It asks us, let me shorten this, yes, okay, so it asks us what is the position of P2 as seen by, let's say, P1. Now position of P2 as seen by P1. So P1 starts to see the position of P2, and P1 sees that okay, P2 is something like this. So in order to reach P2, I have to move 2D towards east. I think you will understand that 2D towards east and 2D towards north. So P1 will say, because P1 is observing, P1 will say that P2 is 2D east and 2D north. Now it brings us to the second question. What is the position of P2? Again P2, not any other particle, the same person P2. But this time the observer is different, as seen by P3. What does P3 say about the position of P2? So P3 has to say that the position of P2 is something like this, and in order to reach the position of P2, I'll have to move first, as you can see, I'll have to move 3 units towards west. This direction is west, the left is west, so 3D towards west, and then a D towards north. So P2 will say, what will it say? P3 will say that P2 is 3D west and D north. Now let me differentiate these 2 answers with a line. Right. Now my first question is, who is the observer in the first case? This is my first case, this is my second case. So the observer in the first case is obviously P1. P1 is saying something about P2, and the observer in the second case is obviously P3, and P3 has to say something about P2. Now the question is the distance, is the position of P2, has the position of P2 changed or it is same? So we can easily say that P2 is a static thing. The person, whoever it is not moving, the person is not moving, so P2 is static, it is not moving. Now if P2 is static, why are we getting two different answers, this and this? If you want to read out the first answer, P1 says that P2 is 2D east and 2D north. If you want to read out the second answer, P3 says that P2 is 3D west and D north. Why are these two answers different? So that brings us to our first rule of relative motion. The first rule, that every observer considers itself to be at origin. And this is very important. So if P1 was observing, as in the first case, you might see in the first case P1 was observing, and when P1 was observing, P1 was the observer, and the location of what P1 thought about its position was that it is at 0, 0, 0. And P1 said, okay, I am at 0, 0, 0. And where is P2 now? So P2 is 2D east and 2D north. But in the second case, this case, P3 was the observer, and P3 thought that it is at 0, 0, 0. And when P3 said, okay, I am at 0, 0, 0, then P2 is 3D west and D north. So the answers are changing because every observer thinks that it is at the origin, and that is the first rule of relative motion. Every observer thinks that it is at the origin. Now we come to the second rule of relative motion, and in order to understand the second rule of relative motion, we must think of something very basic as in the rotation of Earth around the Sun. So we know that Sun is a large object, and Earth is a very small object, and Earth rotates around the Sun. That's what Earth does every time. Earth rotates around the Sun, and this thing, that is something that we have studied like way back in class 4th, 5th, and we know for sure that Earth rotates around the Sun, and that is like most generic statement anyone uses. But what happens when you, let's say, wake up every morning, and what do you say, and what do you read in regular textbooks? The statement that is used is that sun rises from the east. Now we want to compare these two statements and try to understand what is happening. We are saying that the first statement is the absolute truth. Earth rotates around the sun, and it has been proven without any doubt. But every time when we are on Earth, we don't say that we have rotated or we have done something, we have moved. We say that sun rises from the east. And what kind of conclusion are we going to draw from this? I'll draw a conclusion, and that conclusion is very obvious, but I want to think of a different example. So let's say this is a platform, and there is a train coming. So let me remove this. So this is a platform and there is a train coming. So there is an observer on the platform, and the observer will say which train is coming. So that it will say which train is arriving. And let's say if we have a passenger in the train, the passenger in the train will say that which is the next station. And again, what is the difference between these two generic statements? Which train is arriving and which is the next station? So for this observer, it is station is at rest. Station is at rest and train is moving. For this observer, the scenario changes a bit. The train is at rest and the station is moving. And that brings us to our second and the most important rule of relative motion. And that second and most important rule of relative motion is simply this: every observer, that is rule 2, every observer is at rest with respect to himself. To himself, herself, itself, whatever you like to call it. Every observer is at rest with respect to himself, herself, or itself. That means an observer always thinks that it is at rest. That is rule number 2. Alright, so we come to an example here, and let's say we have three things. We have a tree that is obviously growing from the ground, and then let's say we have a vehicle A or something. It is moving with speed A, VA, and then we have a vehicle B. It is moving with speed VB, and everything is observed from the ground frame of reference, that is, a person is standing beneath a tree on the ground, of course, and he is trying to observe the two vehicles. So this motion is being observed with respect to ground, and ground frame is also called as the absolute frame in basic kinematics. And you know, when you'll move on further in your studies, things will change, but for now the ground frame will be called as the absolute frame, because we are not going to change Earth so consistently, except for a few people that we call as astronauts. Now what happens is this person wants to jump to A, so this person somehow jumps to A. So when this person jumps to A, the first thing that happens is that A comes to rest. Now your observer is at A, so the person who is the observer is at A, and A comes to rest. With respect to itself, the person thinks that the vehicle A is at rest. Now what happens to that tree? That tree gets a velocity opposite in direction, and if we write it in vector form, that will be minus VA. What about the car B, or what about the vehicle B? The vehicle B also gets a velocity minus VA in the opposite direction, but it has also its own velocity VB. So there might be two things, either VB is greater than VA or VB is less than VA, but for now we will say that the velocity of B with respect to A is VB minus VA, and velocity of the tree with respect to A is obviously minus VA. And then let's say the same A jumps to vehicle B. And what happens then? So let me shorten this out and let me move this here. So A is now on vehicle B. The first thing that will happen is that B comes to rest. This thing will be at rest, or at least the observer will think that it is at rest. Now what will happen to the tree? The tree will get a velocity in the opposite direction, that vector sign with proper vector signs we will call it as minus VB. And A will also get a velocity minus VB, and it has got its own velocity VA. Now there are again two conditions, either VA is less than or greater than VB, but for now we'll assume the simplest of the cases, that the velocity of A with respect to B becomes VA minus VB, and the velocity of tree with respect to B becomes minus VB. So what is happening here? We can assume a very simple thing, or we can say in very simple words, the velocity of reference frame is transferred to other objects, to all other objects, as a matter of fact, all other objects in reverse direction. Okay, so in reverse direction, that is what is happening here. I want to clarify this term here. Whenever we say VAB, what do we mean? The first thing that we mean, that A is being observed and B is the observer. So the second term out here, the second one out here, this one is always the observer. And we know from rule number 2 that observer is always at rest. So B will consider itself at rest. The B will consider itself at rest. And the absolute velocity of B, the absolute velocity means the ground velocity, the velocity as seen from the ground. The absolute velocity of B will pass to A in reverse direction. So VAB very simply becomes velocity of A minus velocity of B, and both these velocities, let me put things in perspective for you, both these velocities are the velocities that are considered with respect to ground, because ground is the absolute frame that we consider. So with respect to ground, and B is the observer. And I want to specify, I cannot stress it enough. B is the observer, and the velocity of B is subtracted from the velocity of A. That is a simple rule of relative velocities. So this is a question here. Let's say we have a train. You can see a train, 3 wheels, that's the train. It is moving at 70 kmph forward towards east, let's say. And we have a car moving at 50 kmph, same direction, parallel to the train. And there is a person inside this train, and the question relates to the person. So the question simply states that the person inside the train gets up and starts walking at 5 kmph backwards relative to the train. and you have to find out the absolute velocity of person. Find absolute velocity, sorry, velocity of the person. You also have to find velocity of person with respect to car. So let's see. The person gets up and starts moving backwards with 5 kmph. But we have to understand something. This 5 kmph is not the absolute velocity, and I would like to mention again what is absolute velocity. Absolute velocity is velocity with respect to ground. That is something that we are always going to follow in the kinematics thing. So this velocity, the 5 kmph velocity, is not absolute velocity, as you might see that it says 5 kmph backwards relative to the train, and it is asking you the absolute velocity of the person. So we come to our first question. Velocity of person with respect to train is equals to velocity of person minus velocity of train, and that is our formula for relative velocities. And you must understand that all these velocities are vectors. So if you have to consider directions, that is forwards or backwards, you will also consider signs. So let's come to the first term, velocity of person with respect to train. The velocity of person, as it says in the question, is backwards relative to the train, and it is 5 kmph. So when I say backwards, I will write it at minus 5 as minus 5. Velocity of person, absolute velocity, I don't know. Velocity of train, 70 kmph forwards plus 70. Don't confuse with the minus sign here. This minus sign comes from the formula. So please take that into account. The 70 is plus. So what will be the velocity of the person? The velocity of the person will be 70 minus 5. That will be equals to 65 kmph. And you can understand here that this 65 kmph comes out to be positive. That means this particular person who just got up and started walking is effectively traveling forwards. He is not traveling backwards. So that's that. Now comes the second question. Velocity of person with respect to car. So that will be velocity of person minus velocity of car. Now we already know what the actual velocity of the person is. You can see it in red here. So velocity of the person is 65 and velocity of the car is obviously 50. So that would give us 15 kmph. So with respect to the car, the person is moving forwards with a speed of 15 kmph. So these are the few things that we can calculate in a general question of relative velocity. So these are the next type of questions where relative velocity is useful. So the question is very simple. A car is chasing a bike. Find the time after the car overtakes the bike. And let's give some velocities to the car and the bike. So let's say the velocity of the car is anything, let's say 48 48 meter per second, and let's say the velocity of the bike is uh, 28 meter per second, and the initial distance between them is 100 meters. When the chase started, the distance was 100 meters. Now, how do we solve questions like these using relative motion, because relative motion becomes important in these parts? Now, what we can do is very simple. We can look the relative motion either from the reference frame of the car or from the bike. So let's say we are observing the relative motion from the reference frame of the bike. So this person becomes the observer, and we know that observer is always at rest. Now your bike comes to rest and you are observing the entire motion with respect to the bike. The entire motion you are observing is with respect to the bike, and your bike comes to rest. Now, what is the velocity of your car going to be? Now, since the bike has come to rest, so the car will get a negative velocity of minus 28, and it has an original velocity of 48. Or we can simply do this using formula. Velocity of car with respect to bike will be equals to velocity of car minus velocity of bike. So velocity of car is obviously 48 and velocity of bike is 28, so you are going to get 20. Now the entire distance that the car has to cover is 100 meters. Why? Because the bike is at rest. The person who is on the bike is thinking that he is at rest, so the car has to cover 100 meters to catch the bike. So the time taken is simply becomes distance by speed, that is 100 divided by 20, and that becomes equals to 5 seconds. So in questions of chase, the relative velocity is very important. In any question of chase or overtake, you can very easily consider relative velocity with respect to a particular object which is being chased or which is chasing. For example, I could do the same thing. With respect to the car. So with respect to the car. So if I am observing the motion with respect to the car is at rest, obviously, because car is the reference frame, and the bike and the biker or bike, whatever, gets a velocity. Now this velocity of bike with respect to car, can be written as velocity of bike minus velocity of car. So what is the velocity of bike? Now you must understand here that the car is the reference, and that is why we have put car as the second term. The second term is always the reference. So velocity of bike minus velocity of car. So velocity of bike was, we know that what was the velocity of bike? The velocity of bike was 28 and the velocity of the car is 48. So that comes out to be minus 20 meter per second. So the interesting thing here to notice is that the bike is actually traveling backwards with 20 meter per second as observed by the car, and the distance that it has to travel is 100 meters. So time becomes equals to distance by speed, and that is equals to 100 meters divided by 20, and that is equals to 5 seconds. Now we must understand at this point of time that time is not relative, time is absolute. Let me remove this. Okay, so time is not relative, it is absolute in any frame of reference. So if we are observing the motion with respect to, let's say, the bike here, if we were observing the motion with respect to the bike, In the reference frame of the bike, 5 seconds crossed before the car overtook it. Likewise, when we were observing motion with respect to the car, when we were observing motion with respect to the car, also 5 seconds crossed before the bike reached to it. So the thing is very simple, that time either in the bike frame of reference or in the car frame of reference or in the ground frame of reference is not going to be different. It is always going to be same. So that is the idea of time. You have to understand distances are relative, velocities are relative, accelerations are relative, but time is always absolute no matter what reference frame you choose. So this is another question that we need to discuss. We have two cars A and B and both have length of 5 meters. This car has also a length of 5 meters and this car has also a length of 5 meters. Very long cars, I think. And A is just behind B. You can see A is just behind B. Velocity of A is given, that is 25 meter per second. Velocity of B is given, that is 15 meter per second. Find the time taken during the overtake. How much time will be taken to overtake? And the total road distance covered during the overtake. How much road distance will be required for the overtake? So when we are discussing the overtake, you can see the diagram. First you need to see the question properly. B is moving with 15, A is moving with 25, A is just behind B. Both A and B have equal lengths, 5 meters, and now the overtake starts. Now how much time will be required for the overtake? So for the overtake, we do a very simple thing. We take B to be at rest and A to be moving with some speed. And why are we taking B to be at rest? Because we are observing motion with respect to B. B is the observer. B is observer. So what will be the velocity of A? So velocity of A with respect to B will be given as velocity of A minus velocity of B. All the regular shenanigans, and you will get that how much? 10 meter per second. That is the relative velocity that you are going to get. Now when we have taken B to be at rest, the B will remain at rest because B is the reference frame, B is the observer, as you like to call it. This is B, and A moves ahead. A moves ahead. Now the question is, how much distance does A cover in moving ahead? So the A had first got to become parallel to B. So first it had to come up till this point and then move forward up till this point. So coming up to this point parallel to B would require moving 5 meters, and then moving again further ahead would require 5 meters. So the total distance covered by A, relative distance covered by A, is equals to 10 meters. The relative speed is 10 meter per second, obviously. So the time becomes equals to 1 second. That is distance divided by speed. So this is the way to find out the time taken during the overtake. But there was another question. What was the another question? The another question was, find the road distance covered during the overtake. Now road distance is something that is not relative. Road distance is an absolute distance with respect to ground distance. So let's say if B was like this and A was like this, in 1 second B covers, in 1 second, t equals to 1 second because it requires 1 second to overtake. B covers some distance and A also covers some distance, but A comes ahead of B, and that is how we say that A has overtook B. So the total road distance is going to be the distance from this blue line to this blue line, and that is the total road distance covered during the overtake. Now, how are we going to find out the total road distance covered during the overtake? So first we will find out the distance covered by A, and this is the absolute distance covered by A. Distance covered by A. Now absolute distance will be absolute speed into time. So absolute speed of A was, do you remember what was the absolute speed of A? The absolute speed of A was 25 meter per second. So 25 into 1 second, that is 25 meters. So can we say that the road distance is 25 meters? No. I want you to focus very important, and this is very important. I want you to focus really well here. Whenever you say distance covered by an object, then you consider either the distance from head to head, or you consider distances from tail to tail. So the distance covered by A is either from the red mark to the red mark, or the distance covered by A is from the green mark to the green mark. So either the length of the red line is 25 meters, or the length of the green line is 25 meters. 25 meters. But none of them, let me change this. I haven't written 25 meters. I have just written 2 meters. I'm sorry. So this is 25 meters. So either the length of the red line is 25 meters, or the length of the green line is 25 meters. And that is not the road distance. So let's consider one line. Let's consider the red line. So red line, that is 25 meters plus this extra distance here. And how much is that? That is 5 meters. So we will say that total road distance is going to be 25 meters plus 5 meters, and that is going to be 30 meters, and 30 meters of road distance was used during the overtake. Okay, so here is a question. A line of runners is moving with 10 kmph with a distance of 8 meters between adjacent runners. Parallel to the line is a line of cyclists moving with 15 kmph with a distance of 12 meters between adjacent cyclists. With what speed I have to run in between the line and parallel or anti-parallel to them, so that whenever there is a runner on my one side, there is a cyclist on the other. Now this question requires some serious explanation, so I want you to listen to me very carefully. Let's say that this is a line of runners or joggers, whatever you like to call them, and there are a lot of runners in that line. The entire line is moving with 10 kmph. That means each of those runners, either the first one or the second one or the third one, no matter what runner we are talking about, is moving with the same speed. Also, distance between any two adjacent runners is 8 meters. So they are keeping a uniform distance in between them. And then there is also a line of cyclists, and the line of cyclists, among the line of cyclists, the distance is somewhat different. The distance between the cyclists is 12 meters, and the entire line of cyclists is moving with 15 kmph. And these two lines are parallel to each other, so you can say that they are moving on a straight road. On the left end of the road, you can say there are runners, and on the right end of the road, you can say there are cyclists. The cyclists are shown in yellow and the runners are shown in white. And now this is me here. The question very simply says that with what speed, let's say v, I should move, so that whenever there is a runner on my one side, there must be a cyclist on the other side. So it's not like that for example, let's say I am here, let's say so I am here, and you can see if I am here, there will be a cyclist on my right side, but there is nothing on my left side. So that shouldn't happen. So let me remove this. Now coming back to the question, whenever there is a runner on one side, there is a cyclist on the other side. That is the question, and I have to find out the value of this speed v. How much is this speed v? Right. So what do? I start. You must understand that I am the observer. I am the observer. See the question, read the question. With what speed should I move to run in between the lines and parallel or anti-parallel to them, so that whenever there is a runner on my one side, there is a cyclist on the other. So I am observing the motion. So I am the observer. And what is the property of an observer? The very simple property of an observer is that an observer is always at rest. And that is why I am at rest. Now, if I am at rest, what will be the velocity of the line of cyclists? Relative velocity, of course. The relative velocity becomes 10 minus v. Sorry, the relative velocity of the line of joggers. The white line is the line of joggers or runners. Okay, let me correct this. This is runners. And the yellow line is the line of cyclists. So what is their relative speed? Their relative speed is 15 minus v. Now what is the question? The question is very simple. Okay, right now I am here. Let's say this is t equals to 0. And on my one side there is a runner and on the other side there is a cyclist. After some time, when both of these lines move forward, I will be here again, same position because I am at rest, and this runner has moved ahead and the cyclist also has moved ahead. But now there is another runner into place and there is another cyclist into place, and I still have a runner and a cyclist on both sides. So when the next one comes here and when the next one comes here, they must come here by my side at the same time. So the time required for this runner to come to this position and the time required for this cyclist to come to this position, let's say this time is t1 and this time is t2, we must have t1 equals to t2, as simple as that. So what will be t1 equals to? T1 will be equals to simply distance by speed, and you know that the distance was how much? Okay, alright, so the distance was 8 meters here. I want you to see the distance was 8 meters here and 12 meters here. So back to our question, right? So the distance was, this distance was 8 meters. So 8 meters divided by the relative speed, that is 10 minus v, and that is equals to t2. And how much the distance was for t2? That was 15 meters. Sorry, not 15 meters. That was 12 meters. And the distance was 12 meters divided by the speed, that was 15 minus v. So I guess you have a scenario here. You can cancel out these things to solve 2 times and 3 times. So 30 minus 2v equals to 30 minus 3v, and you can see 30 and 30 gets out of the scene, and you'll have v equals to 0. So that means I should be at rest. I should be at rest. I should not be moving at all. V equals to 0. And let's see how that checks out. So if I'm at rest, what would be the time required for this runner to come over? That will be 8 by 10. And what would be the time required by this cyclist to come over? That will be simply 12 by 15. So if you, I guess, simplify the things, here is the simplified ratio is 4 by 5, and here I guess the simplified ratio is also 4 by 5. Yes, and that is why we can say that the time is same, and that is why the speed should be 0.